Ladies and gentlemen, it's a pleasure for me to give you an insight in a little bit different propulsion. So if you see our propellers, it looks different than any other propellers. First, some words about myself. I am the R&D manager of Voith Turbo Propulsion. I'm a naval architect, and I did already my PhD about Voith Schneider propeller, so I'm more or less working close to 40 years on this propeller. I have dedicated my business life to this propeller, and luckily also in New York is sailing a ship type, the Ollis class with these propellers. If you look carefully, you see them here. We did the underwater hull development and the propeller itself. And so our main product is the Voith Schneider propeller, where you see a sectional drawing, but we have also developed, and we are the pioneers for a special rim propeller, a very silent bow thruster, and a propeller for fast vessels, the Voith linear jet. But I will focus here on the Voith Schneider propeller in this lecture because it's really unique. And I have 4 major points. Who's Voith? Just short, then I will show you some vessels propelled by Voith Schneider propellers, and when we go deeper into the Voith Schneider propeller, the abbreviation is VSP, and I will also tell you a little bit about our R&D activities. The Voith group consists of 3 divisions, so we are a bigger company. We have, as you can see here, more than 22,000 employees and a turnover of around 5.5 billion euros, so it's similar to $2. And our main divisions are Voith Hydro. We are producing water turbines. Second division is Voith Paper, where we are producing paper machines. And the third division is Voith Turbo, where we are part of, where we are producing propellers, but also special drives for or gears for trains, for buses. So this is in our core is engineering, and as you can see here. And so since 150 years the company exists, and we were always keen in developing new technologies. Here you can see a timeline of paper machines, or for example, new turbines like the Kaplan turbine, or here the Niagara turbines here in America. And also we started with the Voith Schneider propeller almost 100 years ago. We developed, I will come to this later a little bit more, to a special tug type. It's called the Voith water tractor. Then this Voith inline thruster, this is this rim drive, the linear jet, and our latest development is an electrical gearless propeller. And the man who invented the Voith Schneider propeller is Ernst Schneider from Austria. He was, as you know, a student. He actually never, what I cannot recommend, never became a real engineer. He felt as an inventor, and he had the idea of a very different propulsion. And he filed a patent and came in contact with Voith. And his first propeller was this model that convinced company Voith to invest in his idea. And then the first vessel, Torqueo, that is Latin and means I'm turning, was already sailing in 1928. And so the propeller, as I said, is almost 100 years old. And the first boat, our propeller number 1, is 1928, and currently we are producing propeller 5,434. So many vessels, also in the US, sailing with this propeller type. And the propeller changed. I have here 90 years of development. On the left-hand side, you see the propellers with almost 300 kW input power, and you see here two guys standing here, and you see the size. And here a new propeller of current times, And obviously a lot changed, not only in the design itself, but also in the hydrodynamics, efficiency, and important points. If we look to vessels, when a little bit later I will go in detail, but I can already say now, the main secret or the main differentiation of the Voith-Schneider propeller is that the thrust can extremely fast and extremely precise directed, and so maneuverable vessels needs this. And one is are tugboats. You can see here the propellers in a bow, and here the tugboat is making a bollard pull test. So what is the highest force it can create? So this Voith water tractor, how we call it, was invented. Why? Because here you see a typical tugboat accident in the 1950s years, where the tugboats were not very maneuverable in bow position, and many sailors died. And the revolutionary idea of Voith company, of Mr. Bear, the inventor, was to bring the propeller in a bow area and the towing gear in a stern area, that we have a lever to direct the vessel better, to create better ship assistance forces, and this works really good. And nowadays, all types of tugs which do special ship assistance use this principle. And here, this is the tractor concept, where the Voith-Schneider propeller is in the bow, the winch in the stern, and there is a fin which creates in indirect mode high forces. And this was the first Voith water tractor in 1952. Her name was B, and meanwhile we have produced actually now number 1000 for Egypt, for the Suez Canal. And this is an indirect method which was developed also by us, that the tug itself works like an external rudder, and the main forces are not created by the thruster, but are created by the hull and by the fin, so that in case, for example, either the ship needs more ship assistance force or a failure is, then it can be used. A second important applications are ferries, and here I show the ferry which is sailing here. It's the Staten Island ferry, and she has two of our biggest Voith-Schneider propeller, each close to 4 megawatt input power, and the vessel's top speed is 90 knots, what was measured at the shipyard in the south of the US, and you can see here that the propeller can create in any direction very high forces, and the maneuverability is unique. But we can also, this is a big ferry, this is a very small ferry. She is used, there are 14 sister vessels. She's used at the Kiel Canal, the canal connecting the Baltic Sea and the North Sea in Europe. The propeller is, here's another example, also a US vessel in North Carolina, and she is also specialized for shallow water. I show you this later, that the Voith-Schneider propeller offers advantages for shallow water, and I will explain why. Minehunters. Minehunter mean if you have to fight against sea mines, you need a very robust propeller in case you have a shock load, that means a sea mine is exploding. You need a very silent propeller and a non-magnetic propeller, and this is the reason why about 60% of all mine hunters of the world are using Voith-Schneider propellers. So this is a Finnish propeller here in heavy ice condition, and this is the new Polish mine hunter, where currently, because of this terrible war in Ukraine. Also the navies around Russia are building, the NATO navies building new vessels against this threat. Voith Schneider propellers are used also for offshore support vessels like here and windmill installation vessel, where you can see here 3 propellers. And in the bow here is the very first thruster. It's a so-called rim drive, as you can see here. And also is used for, and actually this is an electrical Voith Schneider propeller. It's used in a so-called SOV, service operation vessel. This vessel has the task to bring service engineers, fitters to the wind turbines. And you can see here, this is for us a new application of Voith Schneider propellers, where maneuverability counts and especially dynamic positioning capability. And meanwhile, around 12 vessels are sailing with our propeller. Here also operation in a wind field. And also passenger vessels. This is an example in the US. She's sailing at the Mississippi. It's the Viking cruise vessel with 3 Voith Schneider propeller, a brand new vessel, and with really tough conditions because of debris, locks, and a lot of stuff is there. And the VSP is a robust propeller, and I will explain why. And we are also producing propellers for yachts. Here is our Voith Linear Jet, which is a propeller that has a very high efficiency, and it's a very silent propeller. But if we look to our portfolio, when I said already, we have the traditional Voith Schneider propeller, where the blades are rotating and the energy is transferred via a bevel gear or electrical propeller. We go more in detail. We develop and deliver the electronic control systems. This is the propeller for fast vessels. This is a very silent bow thruster, and this type of thruster can also be used as a so-called inline propulsor, where it's either as a swing-out unit or as a permanent thruster. And here, the Voith Schneider propeller, how does it work? You can see here the position of the blade, and this vector shows the force, and I have a small program which is called IVSP, Interactive Voith Schneider Propeller. You can download it from our website, and it's also in a more advanced version, but where you need a little bit more time, where you can even steer vessels or make a competition. So IVSP is also in the stores of Android and of Apple. And now I start the engine, and the propeller rotates, and the blades, they rotate, but they do not oscillate. And so the vessel here is not moving. And now I have here a driving pitch and a steering pitch. And when I increase the driving pitch, for example, and if you pay your attention to the red colored blade, you see that it's heavily oscillating. And this movement is created by a kinematic, what we call kinematic is a gear. It's a mechanical gear that creates this motion. And if we go now to the force, then, and I stop it here, just to explain it, when you can see here that the propeller creates, or the blade, creates in more or less all position hydrodynamic lift. So it's not a resistance like a pedal wheel. It's a hydrodynamic lift. What is the force? And the lift itself can divide it into components, in a thrust force and in a, let's call it, transversal force. And the transversal force is canceling out on all positions, and the thrust force is added up, so that we come in total to this green vector, and this is the thrust force, and we can change the thrust in its magnitude or in its direction simply by changing the way how the blades are moving. So the phase and the amplitude. I do it now. And we can, for example, go to 0 and to the other direction. And this can be done extremely quickly. Why? Because we don't turn a big screw. We just simply change the amplitude and the phase. And that means we can do it for a very small unit. Let's talk about 200 kW, even in a second, to go from full ahead to full astern. And on a big unit like the Staten Island Ferries propeller, it can be done in about 5 seconds. And so this can also be changed in thrust direction, what I'm doing now, or it can be combined also to have a steering force. A steering force, and we can individually change it. And it can be done also with a joystick, where you have then the combination of rudder and of driving pitch. And so I really would like to encourage you to go to our website, where you find this basic IVSP or an enhanced version. There's a real simulator behind it. That means where are the full hydrodynamic forces, the inertia forces, the hydrodynamic mass forces, and it's very, very precise. It's there are 3 vessels in, and the owner of these vessels, one is a tugboat owner in Norway, one is a ferry owner in South England. They use this as a training tool. So I will go ahead with my slides. And so why this propeller can be used? The propeller has the fastest and most precise thrust allocation. And I come later to other points, rotor stabilization and dynamic positioning. I will explain this later. So I said we are what I would say a very typical German engineering company. And you can see here that the Voith Schneider propeller, the kinematic, the bevel gear, it needs a lot of engineering. It has to be very precise, and it's very robust with kinematic. It lasts for over a decade. So we have propellers in operation, which are, this already explained with the tool, which are in operation already since 80 years. And the propeller has a very low RPM. If you compare the Voith Schneider propeller with the screw propeller, when the RPM is only about 25 to 30% compared to a screw. So it's slow turning, which has big advantages in terms of efficiency, cavitation inception, in terms of reliability, wear and tear. It has 2 disadvantages we openly communicate. One is if you have a low RPM, you have a higher torque. Higher torque means you have to design for a higher torque, the mechanics, and you have more weight. And of course, more weight needs more material, needs more cost. So the Voith Schneider propeller is the most precise, fastest propeller, but also we must honestly say, the most expensive propeller. So these are the 2 drawbacks of the Voith Schneider propeller. And I go over this here. So we have a model test tank, and here this shows also the wake of the propeller, and this video shows how quickly it reacts if we change the thrust from port to starboard, for example. And you see the wake direction, and simply ink is used to make the flow pattern visible. It's really, really simple, and this is done only by changing, I repeat this video, this is done only by changing the way how the blades are oscillate, means the amplitude and the phase of the oscillation. And So how looks the Voith-Schneider propeller? Here's a sectional drawing. The mechanical version, we have the blades, we have the kinematic linkage, whereas we call this control rod. You can think of a joystick, and wherever the joystick is pushed, the thrust is immediately there. So it goes very quickly. Then we have here a bevel gear. Because it turns so slowly, in most cases we have a flanged on spur gear here to bring down the higher RPM of a diesel engine or electrical motor. And then we have two servo cylinders who are bringing this control rod in a needed position to push the thrust. And this is our standard product. And since about 4 years, we have taken away the gear and we have taken away and we instead put in an electrical motor, as you can see here. And so we have now a gearless propeller. And a gearless propeller means we have no losses of gear losses and less bearings we need. It's easy to install. It's a plug and play. You only need the cable to drive the electrical motor. You have less components and it's really a silent propeller. And we use a permanent magnet motor because the permanent magnet motor has a huge advantage. It's efficient not only in a design point, but also in off-design conditions. And this enables the propeller to have less fuel or less energy in any working conditions. And so our concept is that we are producing the propeller, the hydrodynamics, the blades, the kinematics, the way it steers is identical, and it can be supplied by energy either with a mechanical or with an electrical supply, so that the customer can choose. We have a modular concept for our propeller. And here I give you an insight in our production. So this is here the electrical motor. Here are the coils that are important for the electrical force production, and here are the rotor with the magnets, and this is here our test stand where we are measuring vibration, efficiency, we are measuring the heat production, that is very important, and this is here our test bed where the propeller is tested before delivery. And here you can see how it's installed in a boat. It can be mounted either from underneath or from above, and this is the production. And we were really pioneers in, so the people who had long time before me this position, they developed already an electrical propeller in 1930s, at those times not a permanent magnet motor, but a synchronous traditional electrical motor. But this is also important for developments in technology. You have to be there with your development on the right time. It can be too late, it can also be too early. So at those times it worked perfectly, but the shipping industry was not ready for electrical vessels at those times, definitely not for enough. So it was not a commercial success, just a technical success, but now it's also a commercial success for us. And I said we have an advantage in shallow water. This is a ferry in the so-called Wattenmeer in North Germany, where you can see here it can be extremely shallow when the tide is out. And the Voith-Schneider propeller, if you can see it here, has a rectangular swept area, whereas the screw propeller has this swept area. And what does it mean? It means if you have a bigger swept area, then you most likely learn the momentum theory. Momentum theory means the bigger the area for a propeller, the higher the efficiency. In case you have an infinite big propeller, you could go even to 100%, but it is of course impossible theoretically, not considering friction losses, but of course this is impossible. So normally propellers, we are talking about efficiencies of 70%. And in this case here, you can see here that the Voith propeller normally outperforms all other type of propellers because of the bigger swept areas. And so this is here a little bit an insight into our assembly line. By the way, in case you are most welcome in case you make a tour in Europe to visit our production facilities. And you can see here we have a step production, so there is piping and hydraulics. Here's electrical. This is a smaller electrical propeller for a harbor ferry in Hamburg. And so here are step by step, they will be more and more assembled, the propellers. And then here, this is the other, so this is here, this testing, this here. And you can see here we are testing the propeller because for delivery. So here is tested a smaller 200 kW propeller. This is a Navy propeller for Poland, and this is an SOV propeller. So this is how our production look like. And these are the blades. They have a perfect hydrodynamic designs. We use end plates like the wing legs of a plane to reduce the tip vortex. That gives an advantage in efficiency. And you can see here, this is here our proud boss of the production, and what is the size is, of course, not the biggest. Size of propeller, the biggest, as I said, is, for example, sailing here in New York. And this is the rotor casing with the kinematics, how I have shown you in this IVSP tool. Here it looks like in reality. And here you have an impression how the blades are installed. And this is here our production. Looking to the ferry here, to look inside, where we have not an electrical propeller, but with a bevel gear. This is the size of the bevel gear of the propeller, and the lady is showing this propeller. She is designing this blade. She is an engineer in my department, and is calculating the design of the wheel and of the pinion of this bevel gear. This is suitable for a low RPM and for a 4 megawatt. That means we have here high loads on the teeth. And the blades, this is also the designer of the blade. You can see here, this is the blade of the ferry of Staten Island. So, and it's forged chrome nickel steel. It's a very high quality steel, forged and milled and grinded. And then because the forging factories can go only to a certain limit, when we have here an elongation with a special plastic material, which this works very well. And so obviously we are producing reasonable big parts. Yeah, I am the manager of an R&D department, and how we are working. So we are really, I can proudly say, scientifically driven. That means maybe you know this nice equation, let's say the Reynolds average Navier-Stokes equation. We will go not in detail in it, but we have one of the biggest computer cluster in the marine industry. So all our developments, and it's also maybe interesting for you as students, all our developments go through, everything starts with CFD in our development. And then, of course, we come to pressure, to cavitation, to everything what is connected with that. So this is here a closer view to the pressure distribution and flow field of a tugboat propeller, where we have invented such slots to enhance the bollard pull, just an example. And so here, if you look carefully, we do calculation in waves, free surface, of course, and the propeller is working, and also a two-phase cavitation model is there used. And, oh sorry, it's in German. It's a comparison of different propulsion concepts is written there. And so for example, if a customer is coming to us, or we are going to the customer, and is thinking, could be the Voith Schneider propeller a good solution, then there's of course a question. So the Voith Schneider propeller is about 200 to 300% more expensive than a steerable screw propeller. So we are talking not about 10 or 20, but we are talking about 200 or 300%. So that means the engineers in my department, in the R&D department, we have around 200 engineers, and in the engineering design department who making the CAD drawings, the production drawings, we have again 200. So in total we are 20. Sorry, in total we are around 40. When we compare the vessel for the ship owner, for example, here the Voith Schneider propeller against the best azimuth thruster, it's the Kongsberg former Rolls-Royce azipole thruster. And then what does it mean in propulsion efficiency? What does it mean in fuel and core stability? And more or less nowadays all our vessels, I mean all Voith Schneider propelled vessels, going through a process where we do an optimization. We use currently genetic algorithms. So here I show it for the resistance of the double-ended ferry. So we change the design. So we do first many designs and try to find to not to go in a local optimum. And then we do, it can take weeks or months to change the design and find a better one. And here you can see here how we optimize the design automatically in a computer finally to have resistance reduction. So this is the way we work. And at the end, for example, this was a very tough competition which we won. So the propulsion efficiency of the Voith propeller, as you can see here, is 0.568 compared to 0.541. And at the end, the final test is then a model test, a competitive model test. Also, sorry, also there I have some examples to show. So we have an own tank test, an own circulating tunnel in our company that is reasonably big, as you can see. It's around 20 meters long, and the measuring section has an area of 2.2 times 1.1 square meter. And so here we're developing, for example, here with a Canadian ship designer, new tugboats concept we are testing, or we do open water curve measurements. All this can be done here in our tank test. And the Voith Schneider propeller can change its thrust very quickly. So we made let's call it an invention. Can we use the propeller to reduce the roll motion of a vessel? And it was tested first in our tank test. So we have a wave maker, and I show you this video. Here, this is a test boat. We have two sensors here in these boxes. So they are measuring the acceleration when we have a PD controller. And PD, more or less, it's a little bit more complicated, but it's more or less a PD controller. And you can see here the vessel is now heavily rolling, and now we give a signal to the VSP to kill the rolling or to reduce it. Kill is a little bit too high. And now the VSP is counteracting the exciting forces of the waves. And so the vessel is, of course, it has heave. You cannot reduce the heave because the restoring forces are too high, but you can reduce the rolling. And here, for our propellers, we have model propellers, steerable model propellers, what you can see here. And the Staten Island ferry was tested in a model basin in the Netherlands. It's called Marine. And here, this is a Staten Island ferry in a zigzag test, where the question was posed, is the vessel course stable? How will it behave that no unexpected things will happen when the vessel goes into service? So this is a typical test where we deliver the model propeller, the control system, and also an engineer from my department is then doing this test and analyzing the data. Then we have a simulator where we really do with the ship owner. The ship owners are coming, they come with their captains, and then we're discussing, for example, a tugboat. Shall it have 70 tons bollard pull or 80 tons bollard pull? These are the questions which can be answered in our simulator. And this is an example for the Kiel Canal ferry where we do the design, where we do the CFD calculation to make propulsion and resistance, where we make a model test here in our tank to test if the core stability is there. We invite the captains to test, can they do the task in heavy wind, in heavy current. And and then as a result, there's then the ferry. And in case the captain is not happy, when we do the round again, so that we have everything in our hand. So although we just selling a piece of propeller with an electronic control, we do the whole ship design, we do the control, and this is of course for an engineer very, I would call it satisfying to do such a good view of the whole vessel. And of course we do in a year around 25 vessels, so we gain a lot of knowledge in that. And if I talk about special feature, I have explained how the VSP can change thrust from a head to a stern, and although it's a little bit academic, this example, I must admit, but the calculations are correct. Here are a simulation of the motion that we have here, a vessel around 90 meters long, and she gets, this is academic, a force assumed from a wave coming from the bow, coming from the stern, and the propeller has the dynamic positioning task, means keeping the vessel in its position, and here we can go, what I explained, with a force over 0, have you a thruster which has to be turned when it needs time. And this example shows very clearly why the VSP offers the advantage, because you can change the thrust over 0 and keep the position of the vessel much better. If we have here just a deviation of 0.5 meter, whereas if you are too slow because it needs time and you create forces which are hardly helpful or no helpful, then you have a deviation of 10 meters. So this explains it nicely where is the difference. And zero stabilization I already explained, and in a minute I show you, so if we have the exciting wave moment, we can create a stabilization moment very quickly. And for this vessel, this was the first vessel. She is a platform supply vessel bringing goods to the platform in the North Sea. And I will show you this example of the real vessel, how the road stabilization, where I showed already in a model tank how it works. If you look out of the rear window, you can see to the horizon, she's sailing in significant wave height 4 meters. That means some waves are even 7 meters up, and speed is 9 knots, and she's heavily rolling. And she's coming from the Brand field in North Sea between Scotland and Norway. And now zero stabilization is on, and the Voith Schneider propeller can reduce the roll motion, depends of the vessel design, in a range from minimum 30 to 95%. The roll motion can be reduced. Vessels with a low GM, so the distance between the metacentric height and the center of gravity, can much better reduced in rolling. That is correctly for all roll stabilization systems, and I will repeat this video. So the captain has on its bridge just a button which he has to switch on, and then he can really also with a potentiometer adjust how much force he will use to reduce the rolling, and this works at 0 speed, the example I have shown in our tank test, and it works also at any speed, only at the very top speed, not because then, of course, you need all power to gain the speed. And this I go over. And when we're talking about dynamic positioning, it's a very challenging task for the vessel. You can imagine this vessel is doing here some crane operation. You have here a platform, here a platform. So this is with 2 Voith Schneider propeller fitted. It's very challenging to keep position. And so what we do, we have a special model VSPs. Here is a model base in the Netherlands where a research vessel will be tested. And to give you an idea how big are the vessels, here is a guy standing next to the vessel. And and now the vessel, here are, you can hardly see it, here are vents to produce wind. There are waves in and there are currents. So it's really tough condition, and where the owner, it's a Chinese research vessel, the owner demanded that we were able to stay here in this position in model scale for 4 hours before we got the contract. And this is very interesting also how, I would say, science, model testing, and at the end also to sell something goes hand in hand. And here you can see how it's in real life. So this is here really nasty conditions. So we have here up to 6 meter wave height max. We have wind coming 30 knots, and the weather is nasty, coming stern quartering and go up to 90 degrees even. And the vessel is now stabilized by 2 Voith Schneider propeller and in DP. This is the toughest condition you can think of. And then you can see, if you look to the wake, that the propellers are permanently pushing against this condition. And for this task, no other vessel than Voith-propelled vessel. The North Sea has really nasty condition, especially in winter and late autumn, can do this job. And you can imagine how difficult it is to make here the loading and unloading. And again, if you look to the wake of the VSPs, it's go permanently port starboard, as I have shown in the video in a model tank. And now, in a minute, the seamans are coming to, so you can see here hardly rolling, so the rolling is killed, and now relaxed, the guys can do the work, and this is a very interesting example. Look a little bit to my watch. So when we do deep dynamic positioning, what is important is to also have a value in terms of accuracy, and the VSP is changed in a thrust as shown here, and the competitive solution is turning it. And then what we have developed in a time domain, this was a research project. This went over almost 8 years in total to have it now really precise. We can do the ship motions, the weather, the propeller, everything, as you can see here, in a way that the vessel is modeled, the propulsion system, the sensors, the filtering of the waves, because DP systems are acting only on a second order forces. And this is now a way how a Voith Schneider propeller is kept the position, and you can see here what the propellers are doing. They're producing thrust in a time domain, and the vessel has a watch circle, and the vessel of course is big, maybe she is 100 meters long, but the watch circle where the vessel's set point has to be kept is just 1 meter in diameter, and the heading of the vessel mostly is allowed to change it in a way of plus minus 5 degrees. So obviously the vessel is nicely keeping its position, and this is also a task where the Voith Schneider propeller, which is, as I said, very expensive, has its advantage to keep the vessel longer, and that means the ship owner can work more days per year. So at a certain wave height, when another propeller cannot keep its position, they have to stop. And with the VSP, and this shall be my last slide for this lecture, you can see here, this is a so-called capability plot. It means the weather is coming collinear with current from one direction, and you can see here this is 50 meters per second, wind speed 20 and 25, and the waves are in accordance with this increased wind speed. And the bigger this capability window or plot, the higher waves you can deal with, and the longer you can work. And here you can see here the footprint, where the Voith Schneider propeller has a very slow, and a steerable propeller needs a bigger footprint. So this is the point where we do a calculation. And at this point, because I have also to look through the time a little bit. Pat? Yeah. So I will stop here. What is important, and this is also our message, that propulsion, ship behavior is a great task, also for you maybe a great option in your professional career later to go in this direction. And also, although we are a little bit away, we are in Germany, but you are welcome we have permanently students for bachelor, master thesis, for internships. You are welcome to come to us. We are in a nice area in Germany, in South Germany, close to Munich and Stuttgart. And so we have permanently students from all over the world doing work with us. And as you can see here, we have a very scientific approach, and I can imagine you would enjoy it doing an internship or later working for us. And this is also the end of my lecture. Thank you for your attention.